Okay, thank you for introducing me. And I would like to apologize. Yesterday I didn't say 3 to 1 before taking the vote. And I would like to appreciate the organizers for giving me this opportunity to present, and to all of you for being here. My name is Hwang from Hokkaido University, and today I would like to introduce my paper, Focused Correspondence for Point-Gap Topological Basis in Junction Systems. This is in collaboration with my supervisor, Hideaki Obuse. Yes, my presentation will be done in this order. Alright, so in this study, we focused on the localized correspondence for point-gap topological basis, which is unique to non-Hermitian narrative. Focused correspondence refers to a relationship between topological properties of bulk and the edge states appearing in the boundary. So the figure on the right shows the sigma PDC, the spectrum for a system with periodic boundary condition in light blue. And the topological number for point gap is defined as following formula, which represents the winding number. And winding number means that how many times the PDC spectrum goes around the point E on the complex plane. According to this definition, the area where winding number has finite value is shown in gray area. And if we impose the open boundary condition, the Obuse spectrum, namely spectrum for the corresponding system with open boundary condition, appears in the gray area as shown in the red curve. So, localized correspondence for point-gap topological basis requires that Obuse spectrum appear on PDC spectrum and its interior. And it is also required that all the ion states to be localized at the edge of the system under the open boundary condition. Alright, so I introduced the localized correspondence in non-Hermitian system, but here let's recall what was the localized correspondence in Hermitian system. Okay, so it is required that for a system with open boundary condition, the number of edge states to be appearing near the open boundaries should be equal to the absolute value of topological number. So here the W represents the the topological number. So in this case, the number of edge states should be equal to the absolute value of n. In Hermitian system, the localized correspondence is extended to the junction system, which is composed of materials with different independent topological number. For a junction system, the number of edge states should be equal to the difference in topological number. In this case, the number of edge states should be equal to the absolute value of n minus n. For a junction system, however, the localized correspondence for point-gap topological basis has not been discussed so far, as shown in this table. So therefore, our purpose of this study is to extend the concept for localized correspondence for point-gap topological basis in junction systems. First, this is a model we use in our paper. The entire system is composed of two subsystems, subsystem 1 and subsystem 2. And whose Hamiltonian is denoted by H1 and H2 respectively. Each subsystem is one-dimensional tie-binding model, namely the Hatano-Nelson model without disorders, with gamma representing the degree of asymmetry copy, and the epsilon representing the on-site potential. And please note that for each subsystem, the parameters T, gamma, and the on-site potential epsilon are just constants. And the third term of Hamiltonian, HBC, is representing the boundary condition. And as you can see, it's connecting the two ends of a subsystem and those of the other, creating the junction system with periodic boundary condition. So hereafter, for explanation of localized correspondence, we assume that each subsystem is independent. And we consider the single subsystem with periodic boundary condition as shown in this figure. By Fourier transform, spectrum for each single subsystem with periodic boundary condition is given by a derived on complex plane, centered at its corresponding on-site potential. So point F is often at the point inside each ellipse. And if we define the winding number for a subsystem as follows, it will be simply the sign of the gamma. Maybe either +1 or -1. Further, if we define the difference in winding number, the delta W as follows. And if we consider the case where both gamma 1 and gamma 2 are positive, the area where the delta W is non-trivial is shown in this gray area. Let's call this case 1. In this case, the direction of a symmetry hopping is the same. And second, if the direction of a symmetry hopping is different, maybe if the sign of the gamma are different, as in the case 2, the gray area will be shown as follows. But in today's presentation, for an easy explanation, we will only consider the case 1. And please note that the delta W will play an important role for explanation of Walker's correspondence. All right, so this is in this paper we analytically solve the eigenenergy and the corresponding eigenvector psi of Schrödinger equation for junction system with period boundary function. And our derivation is based on the extension of non-Hwang theory to the junction systems. For Schrödinger equation, we obtain two reconciliations for both reason as follows, where E1 and E2 are defined as eigenenergy minus its corresponding on-site potential. Looking at the range of site number n of two reconciliations, it is evident that the four sites at the interface are excluded. This will give the boundary conditions later. Anyway, without loss of generality, we represent E1 and E2 as follows, with x1 and x2, which are on and inside the unit circle on the complex plane. From these two reconciliations, we have the corresponding characteristic equations. So consequently, the wave function is, the general solution is obtained for complex constants phi. You can see that the general solution is represented as linear combination of two numbers powered by n. That's because there are two solutions that make the characteristic equation 0. Right, so next we have four boundary conditions, which we previously excluded in Schrödinger equation. By applying the general solution to these boundary conditions, a 4x4 matrix is derived, and this matrix makes the column vector of phi geovector. Let's call this matrix A. For non-trivial values of phi, the determinant of A must be 0. While we could analytically calculate for all the cases due to the time constraints, let's consider only the case where L1 and L2 are positive. And L1 and L2 corresponds to the absolute value of x1 and x2. And if we recall the relations between eigenenergy and E1 and E2 and x1 and x2, we can express the eigenenergy as follows. So here, the condition that both L1 and L2 are positive forces the eigenenergy to be complex. So we are now considering four complex eigenenergies. Since the determinant of matrix A must be 0, we derive a specific equation as follows. For simplicity, we consider the case where each subsystem has the same number of sites as L and the same sign of the gamma as positive. And alpha and the beta are defined as follows, which are quite complicated, but the key point is, similar to the non-Hwang theory, we aim to find solutions that give continuous energy. For example, if this part, which is underlined in red, has finite value, the right-hand side of this equation either converges to 0 or diverges when the system size goes to infinity. Then we cannot expect the eigenenergy dependent on L. Therefore, we conclude that this part must be 0. In other words, L1 plus L2 must be equal to gamma 1 plus gamma 2. The simplest solution we can think of is when L1 matches that gamma 1 and L2 matches gamma 2. This would be the simplest solution. And if we apply the L1 and L2 to the eigenenergy here, exactly here and here, then it perfectly matches the PVC spectral subsystems we previously saw. Right, so if such solution exists, it corresponds to the eigenenergies appearing at the crossing points of PVC spectra of subsystems. But this is actually just some part of the entire possible eigenenergy. So with real parameter kappa varying within the allowed range, for example, if the value of kappa is positive, then you can see that this list shrinks and the other expands. Then the spectrum for junction system would form a curve connecting their intersections. This is an actual numerical result for junction system. The PVC spectrum of junction system obtained through numerical diagonalization with the parameters here, it is plotted in gray. And the gray area indicates that places where the W is non-trivial. And then the W, the difference in winding number is defined as follows. For example, if you move the value of kappa from 0 to the positive direction, the eigenenergy moves from the crossing points of PVC spectra gradually towards the inside of PVC spectrum of subsystem 1 and outside of PVC spectrum of subsystem 2. From the fact that the two ellipses with same color do not simultaneously shrink or expand, we can infer that the PVC spectrum of junction system cannot exist outside gray area. So this shows the PVC spectra of junction systems. And figure C in the bottom left is the same spectrum for the junction system we saw previously. The difference in four figures is difference in on-site potential, varying the distance between PVC spectra. If the on-site potential epsilon2 approaches infinity, each PVC spectrum of subsystem will move far from away on complex plane and become isolated from each other. Then, from our intuition, it is expected to be an independent Katamanasa model with open boundary condition, and the spectrum would form an energy band, two energy bands on the real axis. In figure A, the distance between PVC spectra is finite at 8, but even at that distance, it matches our intuition. As we can check, there are two energy bands on the real axis. As we move to the subsequent figures, the distance decreases, with figure D showing the center of PVC spectra by 1.7. The gray area indicates that places where the W is non-trivial. In all the cases, without exception, the PVC spectrum of junction system appears in gray area or its boundary. So we can establish the voltage correspondence as follows. So up to this point, we have looked at the spectrum. Next, let's explore the wave function and localization length. Similarly, while we could analytically calculate for all the cases due to time constraints, let's consider the same cases. Namely, only consider for complex eigenenergies. If we apply the L1 and L2, which are connected by kappa, into the general solution, we obtain the wave function as follows. Additionally, apart from the interfaces, the wave function is approximated roughly as follows. So, for the sites corresponding to subsystem 1, the absolute value of wave function is proportional to exponential kappa n, and exponential minus kappa n for the other sites. And again, please note that this analytic calculation is only for complex eigenenergies. It's also in here. Right, so as it's shown in this figure, we will examine the behavior of wave function around the interface at n equals L. And as shown at the bottom, there are two asymmetric hopping in the same direction, as indicated by these arrows. Let's consider the wave function for eigenenergy existing inside the PVC spectrum for subsystem 1, especially the complex eigenenergy. In this case, since subsystem 1 dominates the corresponding eigenstates, for the size corresponding subsystem 1, we observe the skin effect that localizes exponentially on the right edge. It's the same direction of asymmetric hopping. And for the size corresponding to subsystem 2, however, despite the direction of asymmetric hopping is localized at left edge. So we should henceforth call this phenomenon non-Hermitian proximity effect. To summarize, even if there are asymmetric hopping in the same direction, the wave function of junction system is localized at the interface. To verify this numerically, we assume that the wave function grows or decays exponentially as shown in this equation. And we calculate the localization length, xi1 and xi2, through the fitting with eigenstates obtained by numerical diagonalization. Here, please note that the localization length, xi1 and xi2, can take negative value, representing the exponential decay. Right, so first, let's see the case of complex eigenenergy. And here, the x-axis, n, is numbered in ascending order of real parts of eigenenergy. So with this figure, xi1 equals minus xi2, which is expected by our analytic calculation, is also confirmed numerically. And remarkably, the absolute value of localization length is actually the same, even though the parameters for each subsystem, for example, T and gamma and epsilon, are different. This is one of the unique properties of non-Hermitian proximity effect. Further, let's focus on the eigenenergies appearing at the crossing points. Since the value of kappa is 0 here, both localization lengths xi1 and xi2 diverge, with corresponding eigenstates delocalized. This result also aligns with our analytic result. Okay, so next, let's shift our attention to the eigenenergies on the real axis. Here we observe that xi1 equals 1 over gamma 1 for all the negative eigenenergies on the real axis. The interesting point is this is actually the same with the localization length of independent Hata-Nesson model with open boundary condition. Meanwhile, the other localization length, xi2, the inverse of it is decreasing as its corresponding eigenenergy decreases. According to our analytic calculations, the localization length xi2, whose eigenenergy is negative infinity, eventually converges to 0, which is logical if you consider the physical meaning. So this analysis can be also applied to all the positive eigenenergy on the real axis. So in summary, we established the voltage correspondence in junction systems with PVC as follows. So we have considered the junction system with PVC, but to clarify the voltage correspondence, we also need to consider the junction system with open boundary condition. So here, by removing the hopping between any two sides of junction system with purely boundary condition, we considered the system with open boundary condition and plotted its spectrum in pink. Considering the places where the W is non-trivial, the Obuse spectrum of junction system appears in places where it shouldn't, making it seem as if the voltage correspondence is not satisfied anymore. But this is not the violation of focus correspondence. Focus correspondence in junction system with open boundary condition is not related to the PVC spectra of each subsystem, but is determined by W jump. W jump is winding number calculated from the corresponding junction system PVC spectrum. So in this case, inside the PVC spectrum, the value of W jump is +1. So we can conclude as follows. The Obuse spectrum of a junction system should appear on PVC spectrum of corresponding system or its interior. In this sense, this can be considered as natural extension of focus edge correspondence. In conclusion, we established the focus correspondence for point gap topological phases in junction systems. Although this conclusion is derived from specific lattice model, as I explained, our result can be considered as natural extension, so we consider the focus correspondence we established can be applied for the other general junction systems. Thank you for listening.
Thank you very much. Any questions?
Okay, you define the Hwang number by using the absolute values of difference of the Hwang number.
Yes.
So, but in conventional settings, like without interfaces, basically the sign of the Hwang number is corresponding to the localization edges. So, for example, Hwang number is positive and negative, and they are differently localized. But are there any such things for interfaces? Is the sign of the Hwang number important in your case?
Thank you for the question. I think, yeah, my answer would be yes. Just the standard is like the way the difference in winding number. We consider whether it is trivial or non-trivial. Then we can predict the spectrum. Yeah.
I see.
Any other questions? Did you say that the delocalized state
Yes.
appears? So what is the condition for the appearance of the delocalized state?
Yes. So for the eigenenergies appearing at the crossing points of PVC spectra for each subsystem, the eigenstate is delocalized. So actually, yes. So considering the simple like homogeneous, the simple harmonious model with open boundary condition. So the spectrum, OBC spectrum for corresponding system will be formed energy band on the real axis, right? But in the explanation of focus correspondence for point gap topological phases, I put this word almost. It means that if the OBC spectrum touches the PVC spectrum, then the eigenstate or the eigenenergy would be delocalized. So that's the reason. So in the case of junction system, it also we can also observe that for these eigenenergies is actually the intersection of each PVC spectra. That's the reason why the eigenstate is delocalized.
Good. Any other questions? Are there any correspondence between the non-Hermitian proximity effect and the non-Hermitian skin effect?
So the skin effect is, for example, if we also considering the homogeneous, the simple hadron model, we can observe the skin effect at the same direction of the asymmetric Hawking. So in that sense, we can consider the shape of the wave function as skin effect. But for the other side, it localized at the opposite side of the asymmetric Hawking direction. So we henceforth call this phenomenon non-Hermitian proximity effect. So for example, if we see for the eigenenergies inside the PDC spectrum of PDC spectra of subsystem 2, then the subsystem 2 dominates the entire system. Then it would be localized at the right edge of subsystem 2 and the left edge of subsystem 1.
Thank you very much. Any other questions? So now time is over, so let's thank the speaker again.